Okay, so today's technologically has been a train wreck. So I tried to record Zoom, that didn't work. I tried to record third block, and that worked well until the camera fell over, and then I lost like the first half of the recording. So this is going to be something I'm going to push out to my honors physics classes and my AP physics. Okay, so because the beginning of it is the same, I conveniently recorded the second half of my honors physics class. So listen to me, honors physics class. You are going to have 2 additional videos to watch that cover force and acceleration and some graphs, okay, that I will send out to you all separately. Just bear with me. It's been a day. And then I thought I had this cool microphone thing going that went through my speakers, and I thought that was amazing and it was going to work well. And then the kids that were on Zoom were saying, we can't hear it because of where the microphone is, so then I had to take that off. And now I'm back to talking like this again, and so my voice is going to be trashed by the end of the day. So it's been a good day, but we'll get through it. Okay, so let's talk about the lab. And let's start with this. Hopefully that first lab that you have, or first graph. Dear Lord, if this thing quits working, I'm going to scream. Technology is really good when it works.
Yeah,
But right now,
It's not
technology is not
working.
my friend. Oh. Because it's been a day.
I can tell.
Let's try this.
We're good.
It works for now. Okay? It works for now. We'll take that as a victory.
Yeah.
All right, so the first graph that y'all are going to have is you're going to have a graph of force in newtons here and elongation here, okay? So here's the first thing I'm going to look at, okay? On your first graph, we put force here because that was our independent variable because that was what we control. You put elongation along the y-axis because that's the only thing that was dependent upon, that elongation was dependent upon that value of force. So you're going to draw a line of best fit and make sure that you've come in here, and this is the easiest points you're going to get in this class. Make sure that you went in here and you wrote down and circled those points that I'm going to use to find your slope. Okay? These are the easiest points you're going to get in this class. Don't miss them. Because everybody's line of best fit is different. And then you're going to show me how you got your slope. So what I'm going to look for is some number of meters minus some number of meters over some number of newtons minus some number of newtons. Okay? Put in the units. Don't wait until the end. And when you get done, I want this as a fraction, as a decimal. Do not leave this slope as a fraction. Change it into a decimal. And it's probably going to be something around like 0.02. Okay, that's an ish. And then meters per newton. Okay? That's about where you should, it varies a little bit, but that's kind of close. Now, here's how I'm going to check that you got this right. Here's the first thing I'm going to do. I'm going to go to your graph, and I'm going to find 1 newton. Okay? I'm going to go to 1 Newton, and then I'm going to come up to this point, and I'm going to see where it crosses this line, and then I'm going to come over here. Because that's what the slope of this line should be. So I'm going to start here, go up, go across. That should be the slope of the line. So if you want to see if your slope is right, this will at least give you a ballpark to see if it matches up, because this is what this means. Now, again, you have to understand what the physical representation of this slope means. That means for every Newton of force that you apply, this is how many meters it changes. So if you apply 2 Newtons of force, it's going to stretch twice as far, okay? That's what that slope means. So, do not leave that slope as a fraction, and make sure that you have units on the end of it. Now, when you get to, let's see, back for a second. No, not the graphical lab itself.
Oh, okay.
Thank you. Now, when you get down to number 5, I'm going to say, okay, you want to achieve an elongation of like 10 centimeters, 15 centimeters, whatever that is. So what you want to do is you have the general form of your equation is elongation equals your slope times your force. So what I've done is I've given you that elongation, 10 centimeters, 15 centimeters, whatever that is, okay? Make sure that you pay attention to the units. Here's your slope, figure out what that force is going to be. Now, here's how you can use your graph to see if you got it right, okay? Come up here and find that value of your elongation, okay, whatever that is, 10 centimeters, 15 centimeters, doesn't make any difference. And then come over here and see how much force corresponds with that value. If those two numbers match up, hey, you did it right. If they don't match up, something's wrong. Now, you can't use it to get an exact value, but at least you can get a ballpark idea to see if it's right. Okay? That's just another way that you can figure this out. Now, when you get down to, let me see, when you get down to number 8 and number 9, what's going to happen with the slope of the line if you use a stiffer spring? So here's what you have to understand in terms of how I want these answered, okay? You have 2 variables here. You have force and you have elongation. You can't change both of them, okay, in your answer. You have to keep one of them the same. So in other words, don't sit there and go, oh, with a bigger, more force is required to get more elongation with a stiffer spring. Well, that's true no matter what the spring is. You need more force to get more elongation. So what you want to do is you want to keep one of these constant. So what I would say, and there's 2 ways you can do this. I don't care. It's a personal preference. One option is that you keep the force constant. And you say, okay, hey, what's going to happen to the elongation? So if you have a stiffer spring, if I apply that same amount of force, what's going to happen to the elongation? One of 3 things can happen. It's going to stretch more, it's going to stretch the same, or it's going to stretch less. What's going to happen?
It's going to stretch less.
Yeah. So you would say for a given amount of force, there is less elongation, so what's that going to do to the slope?
It's going to reduce it.
Reduce it. So you want to mention on number 8 3 things. You want to mention force, you want to mention elongation, and you want to mention slope. Okay, so those are the 3 things that you want to talk about when you answer that question. Now, the other thing that you could do, and this is the other approach that you can take. This is a personal preference thing. I don't care what you do. The other option is that you keep your elongation the same. So in other words, I want the same amount of stretch. Okay, I've got to make this spring stretch 10 centimeters. What's going to happen to the amount of force that it would take? Oh, well, if it's a stiffer spring, to get the same elongation, that's going to require more force. That would also make that flatten out. So when you answer a question like this, you want to make sure that you either keep your force the same and look at the elongation, or you keep your elongation the same and change the force. Okay? I don't care. Just pick one. Okay? Now, let's talk about the moon question. So there's three options that you could have on the moon question. The slope is more steep, the slope is the same, or the slope is less steep. Okay? Those are your options. More steep, the same, less steep. So let's do a quick opinion poll. So how many of you have the slope is more steep? You do?
Yeah.
Okay, we have one more steep. How many have the slope is less steep? It's actually the vast majority of you. Okay? How many have the slope is just the same? Okay. All right. You all voted. That's different for Americans. Okay? So, no, I'm just saying it's true. In Chicago, y'all could have voted more, like 3 or 4 times for each one. Okay, so let's talk about this. So here's our spring, right? Here's our spring. So here's what I want you to look at. Okay? Here's what I want you to look at. Let's just say leave weight out of this. I'm just going to grab a hold of this and I'm going to pull it down. Okay, so it's going to take a certain amount of force to stretch it a certain distance, right? Okay? Don't worry about gravity, don't worry about forces, don't worry about anything, okay? Now, we're going to take this thing and we're going to go to the moon, okay? Ultimate road trip, we're going to the moon.
Yeah.
Now, we're on the moon. We're on the moon. And if I grab a hold of that spring and I pull it down, is it still going to take the same amount of force for me to grab it and pull it on the Earth as it does on the moon?
Yes.
Yes. Okay, because how much force it takes is an intrinsic property of the spring itself. Okay? Right? The intrinsic property of that. Okay. So, if I take a 1 kilogram mass on Earth, and I hook that up, so I would to find that force, I would take 1 kilogram, multiply that by 9.8 meters per second squared, and I would get 9.8 newtons. Okay? Everybody cool with that? And it's going to stretch at a certain distance. Okay? Now, if I go to the moon, this still is 1 kilogram because it still contains the same amount of stuff. Okay? So now I'm going to have 1 kilogram, but now I'm going to multiply that by 1.50 meters per second squared. Right? So now I'm only going to generate 1.5 newtons of force. Okay? Now I'm going to generate 1.5 newtons of force. So now on the moon, what's going to happen to that elongation?
It's going to decrease.
It's going to be much, much smaller because of the fact that I'm applying a smaller amount of force. So here's my question. On Earth, if I apply 1.5 newtons of force, I'm going to get a certain amount of elongation. If I go to the moon and I apply 1.5 newtons of force, am I still going to get the same elongation?
Yes.
Yes. So the graph is going to be the slope of the graph is going to be the exact same. Okay? Now, if you have your answer wrong, this is when you can change it. For those of you that are watching in the studio audience, okay, this is when you can change yours. Okay? So, now, what would happen is the data points, if you use the same scale, instead of going from like 0 to 10, you're only going to go from like 0 to 1.5. So your data points would be much closer together, okay, if you use the same scale. But because it's the same ratio of force to elongation, you're going to end up with the exact same sloping line. Okay? Because it's that same ratio. So for those of you in the studio audience, okay, there you go. Okay, so a couple of housekeeping, and this applies to my honors physics kids as well. So I sent you all out an email that has information about taking this class for WSU Tech. So, and this applies to you guys as well. So, there's an email, there's a series of videos and links and things that you need to go through. For you guys, if you know you're going to be an engineer and you have to have the calculus-based physics, okay, it's university physics, K-State calls it engineering physics. Don't take the class for dual credit, okay, because it will not fulfill your requirement because it's not calculus-based. It's still going to make it easy for you when you actually take it, but it's not going to count as that credit. But for those of you that are going into business, law, whatever, okay, you all are going to need a 5-hour lab class. So, or if you're going into chemistry, biology, something like that, where you have to have the non-calculus-based physics, it will fulfill that requirement. So, WSU Tech is going to ding you like $360, something like that. I don't remember the exact number. So you're going to pay $300 some odd for a 5-hour class. You go to K-State, KU, WSU, you're going to pay $300 basically per credit hour. So if you take the same class at WSU, 5 hours, that's going to cost you like $1,500, and you're going to have to probably buy a $150 to $200 book for the class, okay, or buy online access, which is still the same money, which is outrageous. So if you're going to be a non-engineer, okay, or something like that, and every degree requires some type of lab credit, I'd highly recommend taking this class for dual credit. It doesn't make any difference to me, but it's a bargain compared to what you're going to pay for later. Number one, you pay a lot of money. Number two, it's, I hate to say this, but physics teachers at the college level sometimes aren't all the best. They tend to be a little bit boring because it's like, oh, it's a freshman level class and they're not excited about teaching them. So, and you're just going to have to take the class again anyway. So, and even if you have enough credit hours, you always have to have like a certain number of electives, okay? So this could even fulfill just one of your elective credits. So when in doubt, talk to the university that you're thinking about going to, punch in your major, see what classes that you have to take, okay? And if it has, hey, like general electives, or if you have if you have to have physics, figure out if it's calculus-based or non-calculus-based. They'll be able to tell you. Now, in the enrollment process, this is the first time they've ever done this purely online. Most of the time they come out here and do this. So they're not going to, because of COVID, they can't come in here. So with that said, okay, if you have any questions, don't ask me, because I don't understand what the process is going to be. I forwarded you an email from Jordan. WSU is of great help, okay? If you have any questions at all, email her. She will be able to help you out. She'll be able to talk you through the process. I know if you haven't taken WSU Tech credits before, you have to become a student. You have to set up an email and all this stuff, and they can even like set up enrollment and things like that, or where you can like pay online and all that good stuff. But the deadline for this is September 22nd, which is a week from tomorrow. Okay, so go home, discuss this with the parental units. Go, hey, because if it's mom and dad write the check, I guarantee you they'd rather pay $300 some odd in this class than $1,500 later on. So I'm just telling you that might be something to consider. Also, because my emails are starting to get bogged down, and this is a learning process for me too. So when you send in something with that CAM scanner, and because I'm sorting this based upon like my 4th block class, 3rd block, 1st block. So when you send this in, I need you to make one small tweak. I need you to make one small tweak and go, okay, hey, put your last name, okay? And then like for you guys, I want you to put 4, because that's going to tell me that you guys are in 4th block. And then like hyphen, and then like, in this case, spring lab, okay? So just a small tweak, for you guys, put 4. If you guys are watching this and you're in my 3rd block honors physics, put a 3. If you're in my 1st block class, put a 1. If you're taking a virtual class, okay, if you're one of my purely virtual students, put a V. So it's either gonna be a V, a virtual, a 1, a 3, or a 4. Okay? Got it? Good? Okay. So there's that. Okay, now, for those of you that are in honors physics, this next discussion won't apply to you, but you're still going to have to do this way on down the line, so you can pay attention, and then you can say, oh, I remember when Burkamp talked about that in August. So the next graph that you're going to do is that you're going to put force here, and you're going to put elongation here, and you're going to get something that's going to look like this, okay? Force and elongation. And then you're going to find this area here. So when we do energy in honors physics, you will do this graph eventually too, once we do energy. So when you find this area, this is in newtons, this is in meters. So your area of a triangle is 1/2 base times height. So your area is actually going to work out to be units of Newton meters, which later on you'll see is the same thing as joules, which is a measure of energy. Okay? So when you find this area, and again, I beg of you, read the instructions. So one of them, see your data. Okay, so if I'm Lauren, what's your maximum elongation? 0.07? Okay, so Lauren's maximum elongation is 0.07 meters. Okay, whatever that is, that's 0.07 meters. So what she's going to do is she's going to go out here and she's going to find 0.07 meters. She's going to draw this line straight up until it hits the line of best fit. Then that is the point that she's going to use as her height. Okay? It might not necessarily be the same as the amount of force that's been generated. Okay? But you're going to go to, make sure you're doing force and elongation. So you got force over here, you got elongation over here. So she's going to come out here to this point, come up, see where it crosses the line of best fit. That's what she's going to use going across. Okay? Good with that? Okay. Now, you're going to find the slope, and which later on you'll see is going to get you the spring constant. And that's typically around 70 to 80 for these springs. Okay? And here's what's different. The units for this slope are going to be newtons per meter. And like I said, eventually honors physics kids, you're going to find the slope of a line like this too. It's just going to be further on down the line. So here's what's going to be different. You can have slope here, and your area is going to be in Newton meters. Okay? Are we good? Anything else you want me to go over on this lab? This is your time to ask if you have any questions at all. No questions. Okay, so here's how, when you scan this in, okay, again, you're going to put like Hewer for Spring Lab. So I want the lab instructions themselves first. So like the page 1, take a picture of the second one. And then I want the 2 graphs. I want this graph first where you've got the elongation and force. And then if you're honors physics kid, that's the only graph that you have. My AP Physics kids, I want force and elongation. Okay? Are we good? Okay. So, stand up, take a quick stretch, and then we'll talk about the dimensional analysis assignment. Okay.
So I found like all of these numbers that I needed, the slope, and then that's what the exact distance was for that. So I'm just confused how to the area.
Okay, where's your graph? Okay, the area's going to come off this graph. So your base is just going to be 0.07. And your height is going to be, yeah, so it's just 1/2 base times height.
Okay, that's, I don't know why, I just thought because the units were usually split.
Yeah, your areas are just units of meters or Newton meters.
Okay. I was just overthinking it then.
Yeah, don't.
Because I already had the answer.
Don't.
I'm the worst like that.
I can do that here. We send pictures of things back and forth.
We good?
Yes.
I think it's okay. I don't believe it's
And
okay.
then, okay, actually, I have one more question.
Yeah, this is why I don't think it's okay.
For sense, what creates the force that allows the string to stretch, you literally mean the weight, like the literal thing that creates the force.
Yeah, like gravity.
Okay,
That's
that's
what
what
I
I
have to do.
really
Yeah, that's all I have to say.
Really gross.
Do not make that difference.
Sorry.
All right. Everyone still rolling?
Yeah, we're still rolling.
Okay. So again, honors physics kids, this applies to you too, so let's talk about this process of dimensional analysis. Okay? So here's what I find about dimensional analysis. You all are very, very good at punching numbers into a calculator and getting an answer and going, wow, the answer is 12, and the little calculator screen shows up and it shows 112, and it's like an oracle, and you see this as saying, wow, here's my answer. Okay, and you all are very good at writing down 12 because that's what the oracle says the answer is, 12. But you all aren't used to necessarily paying attention to the units. So what dimensional analysis does is that, and the sooner you embrace this idea, the better off you're going to be. Mainly because of the fact that it isn't about just getting an answer. It's about understanding the process that generates that answer. And the sooner you embrace this idea of dimensional analysis, the better off you can be, because that's going to allow you to see how problems fit together. Okay? So, on your sheet, on the front, you have two things that I want to talk about. One is AT, and one is AT squared. Okay? Now, if it's AT on dimensional analysis, you're going to come in here and go, okay, that's my acceleration. That's in meters per second squared. I want to multiply that by acceleration. The second's going to cancel out, and I'm going to get meters per second. Okay, so this is what I'm looking for on the front of that dimensional analysis sheet. Now, if it's AT squared, it's going to be meters per second squared times second squared. Those are going to cancel out, and you're going to get meters. So here's what I want you to see. Okay, here's what I want you to see. If I multiply acceleration by time, I get a velocity of meters per second. Okay? If I multiply acceleration by time squared, I get a distance in meters. And we're going to do both of those a lot, depending upon the equation. So this is the advantage if you write these where they're stacked vertically. It makes it easier to see how things cancel out. Okay? It's much easier to see that. You don't have to, but generally that makes life simple. Okay. So on that back side, let's say that one where you have like distance equals v squared minus v naught squared over 2a. Okay? You guys have it as x. Sometimes it's v. It's the same thing. So here's kind of the level of work that I'm going to look for. Put in the units. Now, on dimensional analysis, don't even worry about that too, okay? It's not going to do anything to the units, literally, just leave it out, okay? It's not part of the story. Do not even worry about it, okay? No, it's not there. So, now, when you actually calculate the numbers, you're going to have to worry about it, okay? But not if you're just doing dimensional analysis, because it's not going to change anything. So then the next step is that is meters squared over second squared minus meters squared over second squared divided by meters per second squared. So what this is going to tell you here is that these all now have the same units. Okay, and that's what's important. I can subtract these. That's all I'm saying. And don't look at this and go, oh, that's going to get 0. No, okay? It's not going to get 0. Okay, it's not going to get 0. What you're going to end up with is the same units out of it. So then you're going to get meters squared over second squared. Now, what I would recommend at this point is multiplying by this reciprocal. Okay? This is a process. You want to show how things cancel out. So multiply that by second squared per meter then you'll see that the second squared cancels out. You're gonna drop out one of the meters, so you're gonna go doink, doink, doink. You get meters, that's what distance is measured. So this is the level of work that I'm going to expect to see, okay? Where you're canceling things out, okay? Good with that. Now, on that one where you have time equals mv over force, on this one, this m is not meters, okay? It's a common mistake that's made. This is mass. So make sure that you have put in kilograms here. If I wanted meters, I would have put X or D or something like that, okay? So that's kilograms meters per second, and then down here you want to put kilograms meters per second squared. Now at this point, you can just lop off these kilograms because they're the same. So then what I would do again, I'd write meters per second down here, and then I'd multiply by this reciprocal, because you want to show how things cancel out. So put meters per second times second squared over meters, boom, 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 you get seconds, that's what time is measured. Okay? So this is a process. You want to show how things cancel out. Okay? All right. Anything else on that dimensional analysis assignment? Yes?
On the last question, big T is just time, right?
Yeah, it's just technically that when you talk about time, you can have little t or you can have uppercase T. Little t is just like how long it would take, you know, Adeline to run a city block, okay? It's just a time. How long is third block? 90 minutes. Uppercase T is something that's cyclical or comes back, like we'll talk about big T in terms of like orbits of planets, okay? Here we're talking about big T because you're talking about a pendulum as it swings back and forth. We'll talk about, like, for example, we'll talk about T later on, or when we can make this oscillate. So big T here would be talking about how long it takes for this thing to oscillate back and forth.
So like a period in a sine graph?
Yeah.
Okay.
Yes, exactly. So, there you go. All right. Anything else? We're good? Okay, so shut that down and make sure that you get that scanned and sent in. Yeah, so now you can stop that.